In this video, I want to review an important fact from number theory, which is a theorem that says if n and k are natural numbers, the least common multiple of n and k can be found by looking at n times k divided by the GCD of n and k. Now, in order to prove this theorem, we also need another theorem that I have assigned a video for you to watch before you were watching this one, and that was about GCDs. That the GCD of any two natural numbers, n and k, can always be written as a linear combination of them. In other words, the GCD of n and k can be written as a times n plus b times k, where a and b are integers, and that fact is going to come into play in the proof of our theorem. So the proof of our theorem, well, what I'm going to do is I'm going to do this. I want to start by letting d be the GCD of n and k, because I don't want to have to keep writing out the full GCD of n and k all of the time. And I also want to let m be n times k divided by d. And my goal in my proof is to show that m is indeed the least common multiple of n and k. And in order to show this, what I really need to do is I need to show two things. I need to show, first of all, that m is a common multiple of n and k. And the second thing is I need to show that if c is any common multiple that is bigger than or equal to, well, that is strictly positive. So let me make that correction. That is strictly positive, then m is less than or equal to c. And I want to observe that this particular thing here, because n and k are both natural numbers and the GCD is always about a natural number, it's worth making a note that m itself is positive. So just about everything except a and b in this video are going to be positive integers. But if I could show these two things, then m is indeed going to be the smallest of all of the positive common multiples, so it will be the least common multiple. So I'm going to split my proof into showing part 1 and part 2. So let's move on to looking at why m is a common multiple. So we are now going to show that m is a common multiple of n and k. Well, what I want to do is I want to remember that because d is equal to the GCD of n and k, that lets me say that n is equal to q1 times d, and k is equal to q2 times d. And because n and k are positive, I do know that q1 and q2 are going to be natural numbers. Now, the next thing that I want to note is that I can rewrite those two facts as follows. I can think about n divided by d is going to be q1, and k divided by d is going to be q2. So I know these two facts. Now look at this. I want to recall that the definition of m is that m is equal to n times k divided by d. So what can I do? On the one hand, I can think about m as being n times k divided by d, but I can rewrite this as n divided by d times k, and that'll be q1 times k. And I can also write m as equal to n times k divided by d, but this time I will factor it as n times q over d, and that would be n times q2. And these two facts do say that m is a positive multiple of both n and k. And I know it's positive because q1 and q2 are natural numbers and n and k are natural numbers. So I know that m is a common multiple. So m is a positive common multiple of n and k. Now we need to turn our attention to showing that m is the smallest of all of the positive common multiples. So we now need to show m is the smallest positive common multiple of n and k. Now, what I want to do here is I want to simply say, let's let C be any positive common multiple of n and k. And I need to show that m is less than or equal to c. And if I can do that, then I know that I'll be able to say n is the least common multiple of n and k. So how am I going to do this? Well, if c is any positive common multiple of n and k, then I know c is equal to s1 times n, and I also know that c is equal to s2 times k. And this is where s1 and s2 are natural numbers because n and k are natural numbers. And so I have to be multiplying them by positive numbers to get a positive common multiple. Now, what else do I know? Well, let's look at this. I'm simply going to say, well, what happens if I divide c by m? Now, what I want to remember is m was defined to be n times k over d. So this fraction, c divided by m, is c divided by the fraction nk divided by d. So we invert and multiply. We have c times d over nk. Now what am I going to do? Well, we want to remember that fact that I talked about right at the beginning of the video. We want to recall that since d is equal to the GCD of n and k, there exist integers a and b such that d is equal to an plus bk. And I am going to substitute this in for d. And when I do, here's what we get. We have c divided by m is now going to be c times an plus bk divided by nk. And I can do algebra on this, so let's continue doing algebra. Cm is going to be equal to can divided by nk plus cbk divided by nk. And gee, here those n's cancel, here the k's cancel. So cm now looks like ca over k plus cb over n. But recall, and I'm going to go back and show you for this in just a second. Remember, we have c is equal to s1 times n and c is equal to s2 times k. So as a consequence, we can say that c over n is equal to s1 and c over k is equal to s2. And so we can rewrite this very, very quickly as follows. C divided by m is now c over k times a plus c over n times b, and that is s2 times a plus s1 times b, and that is an integer. So m does divide c, and that is enough, since both m and c are positive, to say that m is less than or equal to c. And this is because m and c are both positive numbers. So that lets me say that the LCM of n and k is indeed equal to m, and m was n times k over the GCD of n and k. Well, I want to tie this video up with one last fact, which is a direct corollary of the theorem that we've just shown. So, a corollary. Let n and k be natural numbers. Then n times k is just the GCD times the LCM. And the proof of the corollary is a one-liner. We've already seen that the LCM of the two numbers is the product of the two numbers divided by the GCD. So you multiply both sides of the equation by the GCD to get GCD times LCM is indeed the product of the two numbers. And that ends this video.